Good morning. Today, my topic is about the phase control and stabilization of 1T-MoS2 via black titanium dioxide nanotube areas, supporting for the electrochemical hydrogen evolution. And I'm a PhD student in the University of Auckland. My supervisor is Professor Wei Gao and Professor Peng Cao. My report contains three parts. The first one is the research background and the introduction of our work in the HER area. The second one is the research of the phase control and stabilization of 1T-MoS2. The third one is the conclusion. The development of industry and population increasement and the population increasement enhance the dependence on the fossil fuels, and it has caused the environmental issues and global warming problems. Therefore, there is an urgency to develop renewable and clean alternatives that can resolve the current problems and sustain long-term development. There are many methods that can be used as a clean energy. Like hydrogen gas has been recognized as a kind of promising energy. It not only can be used in the transportation and industrial area, but also it can be used as a power generation source. However, most of the hydrogen is currently being produced by the steam reforming of fossil resource. The production route is not only consume fossil fuels with the very low conversion rate, but also emit carbon dioxide. Therefore, a clean and renewable and efficient technology for the HER generation without adding further problems is the key element for the production of hydrogen. As we said, water electrocatalyst, or we call it electrochemical water splitting, or HER, to produce hydrogen has been a clean, efficient, and sustainable strategy to replace the fossil fuels. According to the HER research, the interaction between the catalyst and the reactive intermediate should be appropriate. If the interaction is too weak, too few intermediate bound to the surface of the catalyst, and that will slow down the reaction. While if the interaction is too strong, the reaction product fails to dissociate. The hydrogen cannot dissolved from the catalyst that also cease the reaction by blocking the active site. So the ideal value should be 0, which could exist the highest HER property. After people combine the experimental research and DFT calculation, they find out the relationship between different materials and their HER properties, as shown in the following volcano plot. According to the volcano plot, platinum and platinum-based material has been recognized as the most powerful HER catalyst, which exerts the smallest overpotential under the same current density compared to other materials. However, the price and the short content of the noble metal materials limited the application of them in the HER. Therefore, people start to use the non-noble metal-based material, especially with that we call the transition metal materials, to design the HER catalyst. Our group also focused on the design and application of non-noble metal-based HER catalyst. And there are two main research areas of in our group. One is we call the MoS2 HER catalyst, and the other one is we call the black titanium dioxide supported catalyst. Today, I'm going to introduce the last one, the black titanium dioxide supported 1T-MoS2 nanosheet for the high efficiency HER. As shown in the volcano plot I introduced before, the MoS2 is a kind of material which has really high HER activity, and it's also have been recognized as a kind of replacement that can replace platinum in the electrocatalytic hydrogen production. There are actually two phases in the MoS2. One is called the 1T-MoS2, and another is called the 2H. For the 1T-MoS2, the non-bonding d orbital are unfilled, and there are only 2 electrons distributed in the 4D MO4D orbit. So it exhibits the really specific properties, like it can show the metallic properties, and it allows electrons transfer really fast in the catalyst. And it also have really high HER activity. But for the 2H MoS2, it's a traditional semiconductor. It doesn't have any HER activity, and the conductivity of the 2H MoS2 is quite low. Therefore, to obtain the high active of MoS2 in the HER is mainly to increase the content of 1T-MoS2 phase in the MoS2 content. To apply the MoS2 as the HER catalyst, we need to increase the 1T-MoS2 content, but it's quite difficult because, as I said, there are only 2 electrons distributed in the MO4D orbit. That makes the asymmetrically occupation of electrons in MO4D orbit. So the 1T phase is quite unstable, and it's really easy to transfer to the inactive 2H phase. So to solve this problem, maybe there is a good way is to increase the electrons in MO4D orbit and to stabilize the 1T phase structure. Because we want to enhance the electrons in MO4D orbit, so we do need an electron donator. Our group have researched on the black titanium dioxide for a couple of years, and according to our research, we found that oxygen vacancy in the black titanium dioxide can make a good contribution to the electron donation, and it can be recognized as the electron transfer station. So we are thinking about why not combine our black titanium dioxide with the 1T-MoS2 phase, and then maybe the black titanium dioxide can donate electrons to the 1T-MoS2 phase and make it stable. So we use the anodization and annealing method to produce the black titanium dioxide nanotube areas as a substrate. And we use the hydrothermal reaction to decorate MoS2 nanosheet on the surface of the nanotube area substrate and both in the nanotube itself. It is a really unique structure because by using this structure, the nanotube area substrate can provide more surface area for the decoration of MoS2 nanosheet. Then during the HER reaction, more active state can be exported that can enhance the HER property of the catalyst. According to the Raman and XRD analyzation, we can say that the MoS2 nanosheet contains both 1T and 2H phase. The reason that we combine the black titanium dioxide and MoS2 nanosheet is to enhance the content of 1T phase and stop the 1T phase transfer to the 2H. So it's really important to calculate if the content of the 1T phase has been enhanced or not. So we did the XPS analysis. From the analysis of the XPS result, we make the conclusion that the MoS2 nanosheet decorated on the black titanium dioxide substrate contains 80% of 1T phase, but the MoS2 nanosheet decorated on the titanium substrate only contains 60% of 1T phase. That means the decoration and the help of the black titanium dioxide can make the enhancement of active 1T MoS2 phase in the MoS2 nanosheet. We also find the oxygen vacancy peak here and the titanium 3+ peak here that demonstrate the formation of black titanium dioxide. To further analyze the HER property, we did the LSV test and compared it under the current density of 10 microamp. We got the conclusion that the overpotential of the high content of 1T-MoS2 with the help of black titanium dioxide nanotube Aries substrate exhibits the smallest overpotential. It's around 146 microvolt. And because of the high content, because of the high content of the 1T-MoS2, it also exhibits the smallest electron transfer resistance in the catalyst. And due to the help of the black titanium dioxide nanotube substrate, the active seat that exposed to the electrolyte during the reaction is the highest. We also did the stabilization test, and we found the current density doesn't drop significantly for almost at least 24 hours, because after 24 hours, we stop the experiment. From all this experiment and the analysis, we make the conclusion that the combination of 1T-MoS2 and the black titanium dioxide can enhance the 1T-MoS2 content, and it also enhance the HER properties of the catalyst. To further analyze why the MoS2 stabilization, 1T-MoS2 stabilization can be enhanced during the reaction, we did the DFT calculation. We calculate the system energy of 1T-MoS2 and 2H-MoS2 without the help of substrate, and also the 1T-MoS2 and 2H-MoS2 with the help of black titanium substrate. After the calculation, we found that without the help of the substrate, the system energy of 1T-MoS2 is higher than the 2H phase. That means the 2H-MoS2 is more stable because it has smaller system energy. But after they docked on the black titanium dioxide substrate, the energy of 1T-MoS2 decorated on black titanium dioxide substrate exhibits the smaller system energy. So we can make the conclusion that the 1T phase is more stable after the decoration of the black titanium dioxide, and it's even more stable than the 2H phase. To further analyze how the electron transferred in the 1T-MoS2 before and after the decoration of black titanium dioxide, we did the p-dot calculation. As we explained before, there are only 2 electrons distribute in the MO4D orbit in dxy, dyz, and dxz. And we said if we increase the electrons in this 3 orbit, then the stability of 1T-MoS2 can enhance. So we calculated the electron numbers of 1T-MoS2 before the decorated on black titanium dioxide substrate. We found that the electrons in the MO4D orbit is around 5.32 before the decoration per atom. And after it decorates on the black titanium dioxide substrate, the electrons enhance to the 5.36 per atom. And this is the electron transfer current different diagram. And we can see the electron does transfer from the interface between titanium dioxide and MoS2. So we make the conclusion that after the decoration of 1T-MoS2 and titanium dioxide, the electrons of dxy, dyz, dxz does enhanced, and that's why the 1T-MoS2 can have enhanced stability during the reaction. Then we come to the conclusion that we have provided a new solution to realize the phase control and stabilization of the 1T-MoS2 through introduce the black titanium dioxide electron donator substrate. And the extraordinary black titanium dioxide nanotube not only induced MoS2 generating more 1T phase, but it's also stabilized the 1T phase during the reaction and exposed more active state during the reaction. The DFT calculation always also indicate that the electron of the MO4D orbit enhanced, and thus enhanced the stability of 1T-MoS2. Thank you. Thank you for the help from Professor Wei Gao and Peng Cao, and thank you for all the group members.
Perfect. Thanks, Ting. Very good timekeeping again. Very nice. So we've finished. We've got a couple more minutes before the end of the session, so welcome any questions.
Hi, I'm Vivian here from GNS Science. It's amazing to see you combine 2 different materials into one type of material that can improve the property of the catalyst. So have you found any of your 1T-MoS2 inside of your TiO2 tube, or they're just outside?
I did the TEM test. We can see the MO and S this distribute uniformly on the nanotube areas. So we can say it's inside the MoS2, or it's in the gap between the nanotubes. But it does provide more active surface for the degradation of the MoS2 and enhance the active set.
Cool, thanks.
Hi, Ting. Jeff Waterhouse from just across the road in chemistry.
Hi.
Yeah, I really enjoyed your presentation. Your methodologies and results are really outstanding. So well done.
Thank you.
Yeah. I've got a quick question. It's not about the hydrogen evolution reaction. It's about the carbon dioxide reduction reaction. I mean, currently with carbon dioxide reduction reaction, there's a lot of interest in nanotubular materials to enhance the selectivity for C-to-C coupling reactions. I mean, I know molybdenum sulfide has been used for CO2 reduction, but I wonder if you put copper on your reduced TiO2, do you get C-to-C coupling products? I don't know if you've done this or someone in your group has done it or are thinking about doing this.
I don't know, because I'm focused on the hydrogen production, and I read the papers that the copper have the property to reduce carbon dioxide. So I think it's gonna work.
Yeah, because in the channels inside your tubes, CO2 might not be able to get in there very well. So you get a different pH inside the electrode, and this can promote either hydrogen production or coupling products. So yeah, it's just something to think about. But yeah, your work's very good. So well done.
Thank you.
Hi, Ting. Thank you. That was very interesting. I just had a quick question. Did you analyze the effect of varying the diameters of your nanotubes?
Damage of my nanotubes.
Yeah, the inner diameter.
A diameter of my nanotubes. Yes, I do analyze the diameter of my nanotubes, but I didn't demonstrate here. It is around less than 1 micrometer. The length of the nanotube is less than 1 micrometer, but it depends on the anodization time and the voltage of the anodization. But and also the diameter of the hole is, I didn't calculate the whole size, but I think it depends on the anodization time and the voltage as well. But we can change.
It absolutely does. Yeah. I just wondered if you'd actually tried different sizes. I'm actually going to Jeff's point, actually, that the ratio of how much goes in and how much goes out is affected by, we did some alumina anodization years ago, and yes, it's absolutely right. You can tune them to whatever you want. I just wondered if you tried a different range of sizes and if it made any measurable difference, because it's an interesting variable you can control with great precision.
Yeah,